Welcome back to the course on arithmetic and geometry of curves. In this part of the course, we are going to see now how we can use divisors to provide nice models of curves. So, maps and models. So the idea is the following. So I take still a curve C, which is a smooth, projective, absolutely reducible curve over a perfect field K. So C over K. And I take D, a divisor over K. And I'm going to assume that L of D is at least 2. So in that case, now what I can do is the following. I take S0, so let me denote this number, so remember that we have denoted before R L of D minus 1, and I'm going to take a basis S0 up to SR, a basis of L of D. So what I can do is that I can use each of these functions. I mean, remember that a function, you can see it as a map to P1, but here I want to take them all together at the same time. So I'm going to map a point P to S0 of P, SR of P. So as a point inside PR. And I'm going to denote this rational map phi of D. And the nice thing, as we have seen, is that when we have a rational map and the curve is smooth, this map is necessarily a morphism. I mean, here, of course, I mean, you could have poles. I mean, P could be a pole of one of the SD, but then, I mean, you multiply by the right power of the uniformizer to get rid of this. And you can do it because you are in a projective space. So you can multiply all the component by the same power of the uniformizer, and then you get rid of this indeterminacy. So this is a morphism. And of course, I mean, we would like this morphism to give us a way to represent the curve inside PR in the best way possible. So of course, I mean, if I is 1, then I mean, this is P1, and so we have hopefully a non-constant map from C to P1. And we know that if you are P1, then you're a curve of genus 0, and then you're done somehow. And we know already somehow how to classify, at least over K bar, the curve of genus 0. And now, I mean, so we would like R to be at least 2. So that's the first thing. I mean, we want R to be big. So we want the dimension of D, of L of D to be big. But also now, I mean, if you look at the image of the curve, and let's say, I mean, the image of your curve is not inside any hyperplane inside P of R. I mean, this is called a non-degenerate curve. Then, I mean, you can intersect your image by any hyperplane inside PR. And you're going to get a divisor. And this divisor is somehow, I mean, of course, I mean, what is a hyperplane is given by like one of the coordinates, or like a linear combination of the coordinates, to be 0. It means that you're looking at the 0 of a function in L of D. But the 0 of the function, I mean, it's related to the degree of D. It can't be bigger than the degree of D. So what you would like, and generally, I mean, it is exactly, I mean, the degree of D. But so it means that somehow, I mean, if you look at C and if you intersect it, so it gives like a degree of your image, and it is related to the degree also of D. So we have already understood that it's better to have degrees that are smaller to understand our curves. I mean, this is going to limit, for instance, the number of parameters you need to represent your object. So we want small degree for D, and we want big R. And we have seen that, yeah, I mean, of course, I mean, it's not possible to get the best of the two worlds, let's say. But you get it better when D is a special divisor. So R is big for a given D when D is special. So that's why, I mean, trying to find nice equations for the curve is often related to look at special divisors. Do we know many special divisors? No. In general, I mean, finding a special divisor can be a hard task. But at least we know one. So which is the canonical divisor. So we are going to concentrate on the canonical divisor. Kappa, which is, remember, I mean, it has the property that L of kappa is the genus of the curve, and the degree of kappa is 2g minus 2. Okay? What can we say about this map? Phi of kappa, which goes to C to pg minus 1. I mean, of course, I mean, first, I mean, it is interesting only when G is going to be, well, at least 1, let's say. No, even 2 in that case. Okay. So what can we say? I mean, first, I say that, so phi chi of C is non-degenerate. Why? Simply because if it would be degenerate, it means that it would be inside a hyperplane. But what is a hyperplane? A hyperplane is described by the zero, I mean a linear combination of the coordinates. But the linear combination of a coordinate, it is a regular differential. So a combination or a hyperplane in pg minus 1 is described by the zeros of a regular differential on C. But now if this hyperplane would contain the curve, it means that all points on the curve would be a zero of my regular differential. And then, by consequence, I mean, it would mean that omega would be 0. And that's it. Then, I mean, it's not a proper hyperplane. So that's the first point. Of course, I mean, phi k gives a surjective map from C onto its image. So we would like to be interested to know if phi k is injective. So how do we see if this map is injective? It means that for all PQ, you would like that there is S inside L of k such that S at P equals 0, but S at Q is different from 0. You would need to separate the points. That's what it would mean. So if S at P equals 0, it means that S has a 0 at P. So actually S is not only, so S of P equals 0 means that S is inside L of kappa minus P. Oh, sorry. Yes. Okay, because you can, as it has a 0 at P, I mean, if you know that, I mean, the divisor of S is going to contain P, so if you do P minus P, you still get something which is an effective divisor. What is the dimension of this space? So let's compute it. L of kappa minus P. So degree of kappa, we said 2g minus 2. So this is 2g minus 3. Minus, so I'm using Riemann-Roch theorem, minus the genus plus 1 plus L of kappa minus kappa plus P. So what does it give? It gives me G minus 3 plus 1 minus 2 plus L of P. All right? And L of a point, I mean, there is only, because, I mean, we are not in genus 0, there are only the constants. So this is equal to 1 because L of P is equal to the constant. All right, so this gives me G minus 1. Very good. So it's 1 less than the dimension of L of kappa. Now, what does it mean that there is no function S such that S of P equals 0, but an S of Q is different from 0? It means that each time that S of P equals 0, it should also vanish at Q. So, but this is going to happen. So S of P equals 0 imply S of Q equals 0 if and only if you have the dimension of kappa minus P minus Q. I mean, this Riemann-Roch space should be exactly the same as the Riemann-Roch space of kappa minus P. So you would like this to be equal to this, and we have seen that this is G minus 1. So let's compute again L of kappa minus P minus Q using Riemann-Roch theorem. So 2G minus 4 this time, 2G minus 4, that's the degree, minus G plus 1, plus L of kappa minus kappa plus P plus Q. So this is G minus 3 plus L of P plus Q, and we would like this to be G minus 1. So the conclusion is that we see that it is not injective, so phi k is not injective if and only if there exists PQ on the curve such that L of P plus Q, so I cancel the G, is equal to 2. And it's so important that, of course, we give it a name. So do I give exactly where it is inside the notes? No, sorry. But we say that, so if phi k is not injective, we say that C is hyperelliptic. And when phi k is injective, then we say that C is non-hyperelliptic. So for a non-hyperelliptic curve, phi k gives you, oh sorry, it's not k, it's phi kappa. Phi kappa gives you a map which is injective and surjective, so a bijective map from C onto its image. But is it an isomorphism? It is a morphism, but is a bijective map onto the image necessarily an isomorphism? And the answer is not. I mean, we have already seen somehow an example. I'm just going to do this example a bit again in that direction. I mean, remember that we had seen that we have a map from P1 to E, where E was y squared z equal x cubed. And it maps uv onto u squared v, u cubed, v cubed. So it's a non-constant morphism of projective curves, so it has to be surjective. So the surjectivity comes from the fact that it is non-constant, and that was also a proposition that was in a chapter before. It's the proposition 3.2.2. And what about injectivity now? So let's assume that you have two u and v such that the image are the same. So I'm going to distinguish two cases. The first case where I can assume v equal to 1. Then I'm looking at u square, u cube 1, and I'm wondering if this is going to be the same as u prime square, sorry, there is no, this, it's an affine point, u prime cube and 1. But if you look at this, it means that if you do u cube over u square, it should be the same as u prime cube over u prime square, but this is u prime, this is u, so the points are the same, and of course, for v equals 0, you have only u equal 1, so I mean, you're done as well. Okay, so it's an injective and a surjective morphism. P1, I mean, is smooth, so this is always a morphism, but it is not an isomorphism. Remember, I mean, E is singular, so it is not, it is a bijective morphism which is not an isomorphism because E is singular. Okay. So it's not enough. You need something more. And what you need more is that your bijective morphism is actually an embedding. And fortunately, I mean, this can be also measured in a very easy way, because we have seen that, I mean, we want injectivity means that L of P plus Q, I mean, there is no point P and Q such that L of P plus Q equal to 2. And the embedding is going to take just the limit case when you have P which is equal to Q. So why this? Because assume that, I mean, this situation never happened. Then we are in the situation, so, I mean, if C is non-hyperelliptic, then for all P, one has that L of kappa minus 2P is necessarily smaller than L of kappa minus P. So it means that there exists S in L of kappa such that the order at P of S is exactly 1. Good. And now, why is that good? Because remember S, when I embed, when I move C, I take the image of C inside PG minus 1. I mean, the coordinates in PG minus 1 are given by a basis of regular differentials. So such an S, the 0 of such an S is a hyperplane. So what I have is that I have my curve somehow embedded, pushed inside this space, and I have my point P here, and S is a hyperplane that is going to contain the point P, but looking at the zoo theorem in the space, we see that the intersection of this hyperplane with the curve at P at multiplicity 1. So intersection with multiplicity 1. But we said earlier that if a point is a singular point on the curve, then the intersection with any hyperplane that would go through this point would have multiplicity greater than 1. So this proves that P is smooth. And now I'm done, because, I mean, if I have a morphism which is bijective between two curves between two smooth curves, I mean, and it has to be it has to be an isomorphism. Okay, so my map is going to be an embedding. All right. Yeah, I mean, a remark. What I did for kappa, I mean, if you look at the proof, one could replace kappa by a divisor d, and the same proof would give you that phi of d is an embedding if and only if what you have is that for all p on the curve L of d minus p, so divisor d, I mean, well, you need at least, so the map is well defined, so with L of d greater than 1. So L of d minus p, you want this to be always smaller than L of d. So this is a property which is that the linear system associated to d is called base point free. And the second property is that for all p and q in C, you want L of d or L of d minus p minus q to be smaller than L of d minus p. Okay. All right. So I put precisely, I think, I mean, it's going to be the same, and I put precisely L of d minus 2. But I guess, I mean, because of the way it grows, I guess it's exactly the same. Let me check. Yeah. Okay. Okay, and I didn't want to say anything about hyperelliptic here. No. All right. Very good. Now, I mean, let's use this to go to the final step of this first part, is that we really want to get equations for curves of low genera. And let's start with the case g equals 0, so the genus 0 case. Again, I mean, like basically, if I want to stay over my finite, over my field k, I mean, I know only one divisor that would be rational, and it is kappa. And in that case, kappa, it's not interesting because the degree of kappa is 2g minus 2, it's minus 2. So I have a divisor with negative degree, and if I have a divisor with negative degree, there is no function inside, which is not 0. But fortunately, I mean, instead of taking kappa, I can look at minus kappa. So let's look at minus kappa. What can I say of L of minus kappa? So the degree of minus kappa is 2. The genus is 0. I add 1 in the Riemann-Roch formula, and then I have L of kappa minus minus kappa, so L of 2 kappa. 2 kappa is of degree minus 4, so this is necessarily 0, so this is 3. So yeah, I mean, there are plenty of functions inside this space, so this is nice. Let's try to apply the criteria we have here to see if phi of d, or phi of minus kappa, let's say, that would go from C to P2 is an embedding. So let's compute L of minus kappa minus P. So the degree is then 1 minus 0 plus 1 plus L of 2 kappa plus P. This is still of degree minus 3, so this is 2, and I have my first property here. Now, the second property, L of minus kappa minus P minus Q, you see that it's going to work exactly the same way. This is a divisor of degree 0, so 0 minus 0 plus 1 plus L2 kappa plus P plus Q. And this is of degree minus 2, so this is 1, which is indeed 3 minus 2. So it is an embedding. Great. So I have always a model over the field K of my curve C as a plane curve. So we need only to find one equation to determine exactly what is this, this model. So you will see, I mean, if you look at the note in the case of genus 0, then you will see that the proof to show that it is an embedding use other arguments, because, I mean, yeah, then you have two different proofs. The other one doesn't use this criteria. I mean, goes directly checking that you have locally everywhere good properties. So how am I going to find equation? And that's a general trick. The thing is that now that you have found something for L minus kappa, so I'm looking at L minus kappa, I know this is a vector space of dimension 3, so I introduce a base that I call x, y, and z. And now I'm going to look at powers of multiply of my divisor. So what can I say of the dimension of the Riemann-Roch space associated to minus 2 kappa? So kappa minus kappa is of degree 2, so that's degree 4, so that's 4 minus the genus plus 1 plus L of 3 kappa, which is still 0. So this is 5. Okay. But now, what do I have inside the Riemann-Roch space associated to minus 2 kappa? As x is inside minus kappa, x squared is inside minus L of minus 2 kappa. So there is x squared, there is of course y squared, z squared, but also xy, xz, and yz. So all these things are inside. But they can't be independent, because I mean now I have 6 elements, and this is only a dimension 5 space. So there must be a relation between all these things. So there exist constants ai inside k bar, such that well, let me call it a1 x squared plus a2 xy plus a3 xz plus a4 y squared plus a5 yz plus a6 z squared is 0. Which means that if I look at the image by phi of minus kappa of my curve, the conic A1 now with capital letter xz plus a4 y squared plus a5 yz plus a6 z squared vanishes on phi minus kappa of c. Well, that's great, because I mean, as I said, I mean this is a plane curve. I mean, so this has to be an irreducible curve. I mean, and then I mean this vanishes. So we are done. I mean, this is the conic Q. Q is an equation of phi minus kappa of c. So what we proved is that any curve of a genus 0 can be represented as a smooth conic in the plane, and if the conic is smooth, and it has to be absolutely reducible, just by Bezout as well. I mean, otherwise you have singularity. So, I mean, the conclusion is that any genus 0 curve is a plane, or can be as a model over K as a plane absolutely irreducible, or as an absolutely irreducible conic. And conversely, any absolutely irreducible conic is going to be a genus 0 curve. I mean, this is also somehow easy to see. So this is good, and this settles the case of genus 0. I'm going to skip the genus 1 case. I mean, you can find how it works in the notes. I mean, this is a classical case of elliptic curves. And I'm going to jump directly to the genus 2 curve. So for the genus 2 curve, we are using directly kappa itself. Why? Because now kappa has degree 2. The degree of kappa is 2. And L of kappa is G is also 2. So it means that there exists F inside L of kappa non-constant. And I can use this function to get a map from C to P1 of degree 2. Note that I am not in the good case. Of course, I mean, if this map would be an embedding, I mean, then C would be P1, and we have seen that the P1, I mean, they are genus 0 curves. So necessarily, I mean, this kappa, as it is, it has L of kappa equal 2. I could represent it as the sum of 2 points. So I mean, exactly in the case where L of P plus Q would be 2. And we have seen that this is a bad case. So C, so a genus 2 curve is necessarily hyperelliptic. Also, the fact that there is this degree 2 map, we have seen already this case before. And we know that at least when the characteristic of K is different from 2, I can have a singular model for C, which is of the form y squared equal f of x, with f in K of x square free. Can I go further? I mean, because now, I mean, this is not, I mean, we have seen that this is like an infinite dimension family. I mean, f can be of degree as big as you want, and this is not coherent with what we want for the genus. And indeed, you can go a bit further, I mean, and then I invoke another result, which is Riemann-Hurwitz theorem. And Riemann-Hurwitz theorem is a very nice one. I mean, you have the statement and the proof in the notes. So this is theorem 4.3.1. Because it relates the genus of P1 with the genus of C with the degree of the map and with the ramification points of this morphism. And doing this, you see that necessarily the degree of f has to be 5 or 6. So any hyperelliptic, any genus 2 curve is going to be hyperelliptic, and over a field of characteristic different from 2, you have to adapt when you are in characteristic 2, it can be written as y squared equal f of x with f a square free polynomial in K of x of degree 5 or 6. Then, I mean, you could go a bit further and try to say, okay, what about hyperelliptic curves in general? I mean, first, because there exist P and Q on C, such that L of P plus Q equal 2, you have a non-constant morphism from C to P1 of degree 2. Okay? And so we are in the case where you could describe a singular model of the form y squared equal f of x, and using, again, Riemann-Hurwitz, you would find an equation of your curve. But maybe I should emphasize the existence of P and Q here is over K bar, and this divisor has no reason to be defined over K. So which means that over K bar, in characteristic also different from 2, they must be of the form y squared equal f of x with degree of f equal 2g plus 2 or 2g plus 1. What about what happens over K? I mean, over K, I mean, the situation is more involved. I mean, you can also, I'm going to refer to the notes for this case. So this is going to be around lemma 5.4.1, which says that, well, maybe that there will always exist a map, a morphism of degree 2 from C, but not necessarily to P1, but to a curve of genus 0. If you're lucky enough, I mean, we know now that the curve of genus 0, there are the conics. So if your conic has a rational point, of course, we have seen that we can parameterize it and make it a P1. And so we are exactly in the case where you have a y square of equal f of x. So when you are over k bar or when you are over finite field, remember that over finite fields, conics have always a rational point. So you are always in the situation P1. I mean, then you're fine. You're a hyperelliptic curve and you know how to write them. But when you're not over like one of these nice fields, for instance, if you're over Q, then you can have hyperelliptic curves that have a model like this over k bar, but over a field k, I mean, the best you can say is that it is to be a ramified cover of a conic. So this is a bit subtle, you should be careful, and most of the time in the literature you find that it is always, a hyperelliptic curve is always a degree 2 cover of P1. But people say that either because they are geometers and they work over k bar and they don't care, or because they are cryptographers who works about finite fields and they don't care neither. But in general, you have to be more careful. Okay, so let me go now to genus 3. And I'm going now to restrict only to non-hyperelliptic curves because hyperelliptic curves, somehow we have seen them. So now kappa is of degree 4, and L and genus is 3, so L of kappa is 3, which means now I have a morphism from C to P2, and this is now an embedding, because the curve is non-hyperelliptic. So I have an embedding of C inside P2, again as a plane curve. So if it has to be as a plane curve, it is defined by a unique equation, and because we have seen that the degree of the canonical divisor is going to be related as the degree of the curve in the sense of its intersection degree with the hyperplane, we see that phi k of C is smooth quartic. So quartic means a degree 4 plane curve. Is it true that conversely any smooth quartic is the canonical embedding of a genus 3 curve? The answer is yes. So any smooth quartic is the canonical embedding of a genus 3 non-hyperelliptic curve. So how do you prove this? I mean, first you need to see that a smooth quartic is a genus 3 curve. So for this, you use Plücker formula, which tells you that when you have a smooth plane curve, you can compute its genus just in terms of its degree. And so here, the formula tells you that if you take the degree, so if this is 4, minus 1 times the degree minus 2 over 2, this gives you the genus. It's a bit magical. I mean, there is an explanation, of course, but I mean, I'm not going to give it now. So that's 3 times 2 over 2, that's 3. So that's the genus of the curve. And now you need also to see that indeed it's going to be the canonical embedding. And for this, what you do is that you take H, a hyperplane, and you consider the divisor D, which is H intersection with the curve. All right. And I can look at the dimension of L of D. Well, what is there inside? I mean, each time I take another hyperplane, these two hyperplanes, I mean, they are defined by the zero of a linear polynomial, an homogeneous linear polynomial. So the two divisors, they differ by a function. So L of D actually contains all the hyperplanes you can have inside P2. And this is a dimension 3 space. So what you see is that L of D is going to be 3. All right? D also, I mean, because it is the intersection of a hyperplane with something of degree 4, by definition, the degree of D is also 4. So now, let's apply Riemann-Roch. So you see that L of D is 3, and it should be the degree minus the genus we have seen, this is 3, plus 1, plus L of kappa minus D. So this is 4 minus 3, 1 plus 1, 2. So you're missing 1. So L of kappa minus D should be 1. But this is degree 4. This is degree 4. So this is degree 0. And the only possibility for a degree 0 divisor to be of dimension 1, it has to be the empty divisor. So it means that the only solution for this to happen is that actually D is kappa. And you're done. You have proved that, I mean, your curve was actually the canonical embedding of a non-hyperelliptic genus 3 curve. All right, our last task for today is going to look at genus 5. Again, I'm skipping genus 4. I mean, you can find it in the notes, but I would really like to say a bit more about genus 5, because that's the case. I mean, remember, I mean, in my goal, my graal for the whole kind of course and even behind it, I mean, is to look at the question of either a curve of genus 5 with 113 rational points over F47. And as I said, maybe the first nice thing would be to understand this curve. And now we are at that point. We can try to understand this curve and to write equations. The thing is that genus 5, as I said, is already a bit high in complexity with respect to the genus. So we need even more arguments that we had developed so far in the course. So there are, again, like some things that we will need to accept, but I think that you will get at least the general picture. So genus 5. To get equations for genus 5 curves, as we have seen before, I mean, I'm only, of course, going to concentrate on hyperelliptic curves, so I'm going to take the canonical divisor to embed. So where? So maybe let's start with that. So what is the degree of the canonical divisor? I mean, the degree is 2g minus 2, now it's 8, so it starts to be high. And the L of kappa is the genus, so it's 5. And if I take a non-hyperelliptic curve, so now I'm going to look at C inside P4. Okay, so that's already a big projective space. And we have seen that in order to get equations, a nice way to do it is not to look only at kappa, but also to look at powers of kappa. So let's try to be a bit more systematic. And the way to do this is to introduce, so PRD, which is the set or vector space of homogeneous polynomials in R variable of degree D, union 0, if you don't want to consider it. And so the first thing that you could look, I mean, this is a vector space, and the dimension of PRD is D among R plus D. So this is a lemma inside the text, which is lemma 561. Okay? It's very easy combinatoric lemma. And what is more interesting and what is deeper, and here, I mean, I will really need to use arguments that, again, are a bit beyond the materials that we have introduced so far on divisors, is a theorem by Max Noether, which is the theorem 5.7.1, yes. Which says that if C is non-hyperelliptic, then I can look at a map from P RD. So with R is now G minus 1, because I'm concentrating on the canonical divisor. And there is a surjective map from V space to L of D times kappa. And I can describe quite easily this map in the following way. So because C is non-hyperelliptic, I really looked at it as once for all embedded inside my PG minus 1. And now I have this coordinate, so I can look at xi divided by xg minus 1. And this is an element of L of kappa by definition. So if I have this, I can look at any of its powers. So xi to the d over xg minus 1 to the d. This is going to be inside LD of kappa. And of course, I can modify it now by a linear combination. So my map from p g minus 1d to L of d kappa is simply a polynomial p. I'm going to map it on p over x g minus 1d. Okay? All right. And I'm fine with that. And the big result is that this map is surjective. So let's apply this result in the case of d equals 2 for genus phi. So if I take d equals 2, then I have that the dimension of p, so in which g minus 1, so 4, 2 is 4 plus 2 and 2 among this. So it means that this is 6 times 5 over 2. This is 15. And what is the dimension of L of 2 kappa? So kappa is now of degrees 8. So this is 16 minus the genus plus 1 plus L of kappa minus 2 kappa. So this is minus kappa. So this is going to be 0, of course. So 17 minus 5, this is 12. And we have a surjective map. So it means that there is a kernel which has to be of dimension 3. So the kernel of the map dimension 3, which means that there exist 3 linearly independent quadrics inside P4, which vanishes on, well, the image of C inside P4. Okay, so 3 quadrics. So each time I have a quadrix that normally should get rid of one dimension. So one quadric, I have a dimension 3 object. 2 quadric, I have a dimension 2 object. 3 quadrics, I have a dimension 1 object. So I have my curve, and I should be fine. But this works only if the quadrics behave nicely. And this is what we call a complete intersection. So if the intersection is complete, if the intersection of the quadric is complete, then we are done. My curve C is described as the locus of intersection of these 3 quadrics. Is it always the case? Unfortunately not. So it is not the case. if and only if there exists now a map to P1 of degree 3, non-constant map of degree 3, and we say in that case that C is trigonal. So again, I mean, this is a deep result. I mean, this is Enrique Babbage, right? If I'm not wrong with the names. Where is that? Yeah, Enrique Babbage theorem. Or at least part of it, which says that, I mean, it is going to be the case unless you have a degree 3 map. So if you have a degree 3 map, it means that you have a degree 3 divisors that you can write effectively. So there is P1, so a degree D, so sorry, a divisor D, which I'm going to write P1 plus P2 plus P3, such that L of D is at least 2. All right? Is that special in a sense? Yeah, it seems, because if I do now the computation of L of D, okay, I mean, this is going to be the degree, so 3, minus the genus plus 1, plus L of kappa minus D. So this is minus 2 plus 1, that's minus 1, so that's L of kappa minus D minus 1. And I want this to be at least 2. So L of kappa minus D has to be 3. What does it mean? Remember that we interpreted already the fact for section to be in L of kappa minus an effective divisor as the sections which are in L of kappa and which are zeros at the point inside this divisor. So now I want to look at sections which are 0 at P1, P2, P3. So I'm going to look at hyperplanes which go through P1, P2, P3. And I want that the space of this hyperplane is at least of dimension 3. So is that possible? I mean, if you look at 3 points inside P4 and you look at all the hyperplanes that would go through it, you see that it has, if there are just like 3 points which are on a hyperplane, then the dimension of the hyperplanes you can go through this is not going to be 3. So what you want is a special configuration of these points. So this is going to happen. So this implies that P1, P2, P3 are collinear. But now if you have like 3 collinear points on your curve, I mean your quadrics, they would go, of course, I mean they contain the curve. So I mean they contain the point P1, P2, P3. But if they contain the point P1, P2, P3, they contain also the line through these 3 points. And so your quadrics are very special as they always contain a line. So this is not going to be somehow the generic case. Okay. So now, I mean, can we go a bit further in the study of this special case? So in this special case, then I'm going to look at the divisor, which is kappa minus D. So this is going to be my divisor of interest, and L of kappa minus D is greater or equal to 2, but actually, I mean, if my point P1, P2, P3 are different, and I can always assume so, because remember that these points, they come from the pre-image by this map, and I mean, I can always take points which are a point which is non-ramified. I mean, I'm not speaking arithmetically, so over k bars, there are always points like this. So the condition greater or equal to 2 is actually a condition equal to 2. Okay, so I have an L of kappa minus D equal to 2. So what I can do, L of minus kappa equals 3. It's here. L of D is equal to 2. So L of kappa minus D is equal to 3. So which means that now I have a map from C to P2, which is given by this phi of kappa minus d. Okay. What can I do with this map? I can look first that it is base point free. So for this, I take a point D, and I look at the dimension of L of kappa minus D minus this point P. So what is the degree? So this is 8 minus 3, that's 5, minus 1, that's 4, minus the genus plus 1, plus L of kappa, kappa minus kappa, so D plus P. Okay. So the genus is 5, so 4 minus 5, that's minus 1, 0, so this is L of D plus P. And now I'm going to use Clifford's theorem to say that this needs to be smaller than the degree, so 3 plus 1, 4, divided by 2 plus 1. So here it would be 3. But that's the Clifford theorem, like the easy Clifford theorem, and then you have a more precise Clifford theorem that tells you that when this divisor is not 0 or kappa, which is not the case just for degree reasons, and the curve is non-hyperelliptic, the inequality here has to be strict. So L of D plus P has to be smaller than 3, and that's exactly what we wanted for the condition. So yes. So that's the first thing. So I can use it to map to a curve inside P2. And this curve, so the image of C is a curve of degree, which is the degree of this divisor, kappa minus D, which is 5. So I have a degree 5 plane curve. So what is, if it would be smooth, then Plucker formula would tell you that the genus would be 5, so let me think, it's 5 minus, no, plus 1 times 5 plus 2 over 2. So if I have, no, it's the contrary, right? So if I have 3 plus 1 times 3 plus 2, it's 3 minus 1. D minus 2 over 2, yeah, it's D minus 1 times D minus 2 over 2, sorry. Up. So that's 4 times 3, so that would be 6. But no, I mean, it's not, I mean, these images have to be birational, so it has to be, it should be a curve of genus 5, I mean, if it is an embedding. So it is not smooth. But then, I mean, there is a more precise version of Plucker formula that enables you to take not only plane curves, but determines the genus of a plane curve with singularities. And, well, of course, that doesn't mean anything, but inside the birational class of this plane model, you have the curve which is smooth, and the genus of this curve would be given by a precise Plucker formula. And as the genus has to be 5, it means that actually what you have is that your image is a degree 5 curve with one singular point, which is either a node or a cusp. I mean, that's type of singularities. So that's nice. But unfortunately, I mean, all I said till here was based on the fact that I was looking at this divisor D that exists somewhere over K bar. And if I want to do arithmetic, I would like to be able to say exactly the same, but over the field K. And there is a way to do this, is to prove that somehow, I mean, this map from C to P1, not this one, but the previous one, the trigonal map from C to P1 of degree 3 is unique up just to the definition of a change of variable on P1. And so, to prove that we can do this over K means that D is somehow unique. Because if it's unique, then it has to be invariant by Galois. So how are we going to do this? So, well, let's take another one and let's arrive at a contradiction. So let D prime, so a degree 3 divisor, such that D is not D prime and L of D prime is also 2. Okay, so I'm going to take S1, S2 in L of D prime. I mean 2 function, and I'm even going to assume that I have taken them in a good way, such that the divisor of Si, I'm going to denote capital S minus D prime. Okay? And so Si is now an effective divisor. And I want that the support, so the points which are contained inside S1 are completely different from the points which are supported inside S2. Can I do this? Yes, again, because if I look at my degree 3 map, I can, of course, choose a divisor which are not the same zeros as the divisor on S1 and S2. Okay. Such that the zeros of S1 are not are different. So this is one thing. And then one apply what is called the base point free pencil trick. So what does it say? I mean, I'm going to give a version which is adapted to my notation here. So I'm considering L of D, and I'm taking 2 copies of L of D. And to a function T1, T2 inside this sum, I can map it to L of D plus D prime in the following way. I take S2 times T1 minus S1 times T2. It looks a bit strange, but why not? And I want to look at the kernel of this map. So what I say is that the kernel is exactly L of D minus D prime, which I'm going to map to L of D plus L of D in the following way. I take an element U here, and I map it to S1U and S2U. I mean, we can see that indeed, I mean, it works. I mean, it is indeed inside the right Riemann-Roch spaces. And now, if I do this element times S2 minus S1 times this element, this is 0. So, I mean, the kernel is contained, the kernel contains L of D minus D prime. Now we just have to prove that the kernel is exactly L of D minus D prime. So, to prove this, so let's assume we have an element in the kernel. So we have S2 T1 minus S1 T2 equal to 0, and we need to prove that indeed T1 over S1 is inside L of D minus D prime. If I do that, I'm fine. Of course, you have to do it for T2 minus over S2, but this is symmetric. So the divisor of Ti, I'm going to write it the zeros minus the poles. So I have, because Ti is inside L of D, Zi minus Pi plus D, which is effective. And this implies that D minus Pi is effective because I'm assuming that the point inside Z1, Zi are different from the point inside Pi. And what more, and now since S2 T1 equal S1 T2, it means if I write in terms of divisors that S2 minus D prime plus Z1 minus P1 is equal to S1 minus D prime plus Z2 minus P2. Okay. And now I'm going to look at the divisor of Ti over S, T1 over S1 plus D minus D prime. So this is Z1 minus P1 minus S1 plus D prime plus D minus D prime. So what is left? We have minus P1 plus D, so D minus P1 that we know to be effective. Then I have Z1 minus what is left, S1. Okay, and that's the only thing which are left. And I would like to show that this is effective. So the question is that effective? And the answer is yes, because if you look, I have required at the beginning that the zeros of S1 are different from the zero of S2. Remember the supports over there where the intersection was empty. So any zero of S1 has to be inside the zero of T1, which means that Zi minus Z1 minus S1 is indeed effective. So this function is inside L of D minus D prime. Okay. So the conclusion of all this is now that the map is going to be unique. Let me just conclude. Now the argument is easy once we have this thing. Because, so since D is distinct from D prime and of the same degree, we have that L of D minus D prime has to be 0. So it means that this map is injective. So we have an injection of LD squared inject inside L of D plus D prime, which implies that L of D plus D prime is at least twice the dimension of L of D that was 2. So this has to be at least 4. But again, L of D plus D prime has to be smaller by Clifford than the degree, which is now 3 plus 3, 6 over 2 plus 1. So that's 4. But again, the precise Cliffords tell you that the inequality is strict, and I have a contradiction. Oof. All right, so that's the thing. We can always also, so the conclusion of all this, maybe I will write it here. Because, as I said, I mean, Genus 5 is somehow our target object. It would be maybe nice to summarize the situation. So Genus 5, either they are hyperelliptic, and now we know at least, or in characteristic different from 2, I mean, over finite fields that we can write them like y squared equal f of x with f degree of f, we said that it has to be 2g minus 2, so that's 2g plus 2, so that's 12 or 11. Okay, or they are complete intersection of 3 quadrics in P4. Or they are trigonal and represented, or an singular model, singular plane model is over K, so that's the important point that we get now, is kinetic with a node or a cusp. And as this node or cusp is unique, it is also defined over K. That's also a nice property. All right, so that's our object. And I just want to conclude now. I mean, we are now over finite field K, which would be F47, let's say. And we could say, I mean, like the basic way to address our problem would be to enumerate all these objects. Now we have equations, that's a finite set of possibilities, and we could try just to enumerate all of them. So if we do it like naively, I mean, let's take, I don't know, let's take hyperelliptic, I mean, degree 11 or 12. I mean, how many parameters do you need? Like to describe a degree 12 polynomial, you need 13 parameters. So 13 parameters means that you should look at 47 to the power 13. And roughly, so what does it give you? I mean, let's do it even nicely. I mean, for 47 is bigger than 32. 32 is 4, 8, 16, so it's 2 to the 5. So that would be greater than 2 to the 15. I am right. No, 65. Okay. So 2 to the 65. Is that big? Yes, I mean, it's huge. I mean, this is almost what you want when you want to have something which is cryptographically secure. Maybe that doesn't tell you anything, but I can tell you in a way which is much more concrete. If you just wanted to perform on a computer 2 to the power 65 operations, basic operation, this means that in order to, I mean, you know that, I mean, when you use a computer, then it gets hot. So you need to refresh it. In order to refresh it, or like the quantity, let's say inversely, the quantity of energy that would be spent by your processor, all this energy is enough just to vaporize an Olympic swimming pool. So just to do this computation, I mean, and even like I'm speaking basically, you would need to vaporize a swimming pool. And it's even worse, of course, for 3 quadrics in P4, because if you just do it naively, then you have 45 coefficients. This is huge. 47 to the 45, you can't do it. And plane kinetic, I mean, it has also plenty of coefficients. Of course, you can say, yeah, but I could play on isomorphism classes and change by some changes of variables. And if you do it nicely, then you can reduce the number of parameters. But there is something like there is a lower bound. You can't go too low. I mean, Genus 5 curves, there are many of them. And what you can prove, I mean, like it's based on moduli theory, is that the number of parameters needs to be at least 12. So we are very close to cryptographic size, and if we have not more information on our Genus 5 curves, then I mean, this is hopeless. Or you're super lucky, and then you just pick one, and it's the one which is going to have 100 circuit points, and that's sometimes a game that people do. They pick curves, or they try a huge amount of them among some they think that might be the good ones, until, by luck, they find one. But My bet is that we will not be lucky if we do like this. We need more information, and that's a bit all the purpose of the course, of the full course, to have all this information at hand.